Well, good morning. My name is Henry Vanderbilt. I'm going to be a minute setting up here, and then we are going to get underway the transportation and logistics session. Bear with me for a second. All right, our first slide, larger than life. First, a quick mention of style. I'm a firm believer that it's cruel and unusual punishment to make an entire panel sit up for the entire session under the stage lights. We're going to call our panelists down more or less as we need them and let them sit back in the audience and heckle the rest of the time. With luck, we'll end up on schedule with enough time to all come up here at the end and do a back and forth and Q&A session. As far as the panel goes, one of our panelists was not able to make it, John Goff of Aerospace out of Colorado. Apparently his kids are still helping improve his immune system by passing him bugs. You wouldn't think they'd be doing that at this point, but apparently they still think they can perfect it for him. John was going to talk about interfaces and standards for operability. A quick plug I promised him. Aerospace is very much a good outfit to go to if you want things like extremely low mass, versatile capture features and grapplers and fluid couplings, low mass versions of reliable ground fluid couplings that you could use in space. Altius, I believe it's altiusspace.com, but I'm sure you can, ALTIUS, I'm sure you can find it on the web if you're a customer for his work. Okay, as far as this session goes, our other speakers, John Schilling, who has spent a good deal of time working for various defense-related space organizations, none of which is here representing, and Dallas Bienhoff, who spent a lot of time working for Boeing, and among other things, they are looking at the issues of cislunar transportation, is currently running his own outfit, CSDC. I believe that's Cislunar Space Development Company. I believe that if you actually want a considerably deeper look at any of the issues than you're going to get here at this discussion today, you should talk with Dallas offline. Money may need to change hands, but it will be it will be worth it. Okay, end of plugs. As far as what I'm doing up here, I may not be the best person in the world to talk about this, but apparently I'm a quick word of thanks, by the way. Ed Wright and Robin Snelson and Robert Smith and their crew have done a really marvelous job of putting this together. I've really been enjoying it so far. I've been learning new things, meeting new people, and hearing interesting ideas, and that's what I come to a conference for. I'd like a quick round of applause for the people putting on this thing. Okay, as far as why Ed may have thought of me when he was looking for this session, at some point in the spring of 1986, I was driving my beat-up 78 Ford Fiesta into Tucson, first time I'd been west of the Mississippi in my life, with everything I owned that I cared about piled up in the back, showing up at the offices of the L5 Society to run their computer operation and straighten it out for them. How many people here do not know what the L5 Society was? A short version, fellow travelers of SSI from way back. Now, they got merged into National Space Institute. They're now part of National Space Society. Different story. But at the time, I was young, enthusiastic. They'd blown up Challenger, and that had motivated me to think that something really needed to be done. It was time to do something new. And besides, I was between jobs in the tech industry, so needed something new. Happened to be hanging around with the L5 people. They were telling me their computer operation needed some work. Next thing you know, there I was driving up in Tucson. I arrived with the naive notion that everybody understood transportation was a key issue and a problem. That was why I was there. It had become obvious that NASA wasn't going to solve the transportation problem anytime soon. I half expected, very unrealistically, that we'd be, experimenting with building rockets in the parking lot. I got there, and over the next couple of months, I discovered something you've all seen too, that everybody has a grand scheme for what to do in space, and at the time at least, everybody was counting on somebody else to arrange the transportation to make it real. I ended up falling in with a bunch of fellow curmudgeons who thought that, to misquote James Carville, it's the transportation, stupid. More diplomatically, radically cheaper space transportation is pretty much an essential prerequisite for all of the cool ideas we've heard here so far and will hear. If you're doing a construction project in space, you cannot plan the cost and schedule if you don't know how much it'll cost to get the pieces to the site, how long it'll take to get replacement pieces when you break something or forget something, what the lead time will be, what the schedule will be. You need to know all of these things. And more to the point, it all has to be affordable. I and a bunch of people, most of whom were smarter than me, back at the time came up with the thought that the best way to go about this was to change over to reusable rockets, robustly reusable rockets. You send it up on a mission, you bring it back, walk around it, make sure nothing's broken. These days you run the self-diagnostics. If anything doesn't turn up green, you fix it. Then you fill it up with propellant and fly it again. You do this with a small crew, you do it with fast turnaround. Costs start coming down, especially as compared to the old, pull the airliner over to the end of the runway at the end of each flight and scrap it. I mean, we all know that that's expensive. We all know that reusable rockets are the way to solve this because after a couple of decades pushing the idea, oddly enough, it caught on, at least as far as getting to low orbit. There are people here in Seattle and there are people down in Hawthorne who are doing a very good job of making it all real, working more hours than I could ever tolerate. I'm very impressed. They're doing well enough that I actually was able to step back, take a little time off starting a few years ago to deal with the fact that burning the candle at both ends in this business isn't necessarily a good long-term lifestyle choice. But it's gotten to the point where there's an obvious next step. It's getting to the point where we can get to low Earth orbit for $1,000 a pound, and that's going to be dropping. It was $5,000 to $10,000 a decade ago. It's going to be dropping more. That's great. How do we get from low Earth orbit, or LEO in the trade, to where there's a there, to where there's bulk mass to work with to build all these neat projects we all would like to do? The obvious nearby places are the moon, where we're recently discovering just about everything we need is there in some fraction. Nearby asteroids, we're learning more about them too, and the inner planets. The short answer is that old-fashioned chemical rockets are probably the way we need to start out. Electric propulsion is still a niche thing because it's got what I call the mouse fart thrust problem. The power supply is way, way too much, so there's very low acceleration to it, so it takes a really long time spiraling out to get to places. For far-off trips, it's the best way. Nearby, you want something quicker, and so far that's still chemical rockets. Nuclear rockets aren't quite there yet and would be a really big investment, and there's a reasonable school of thought that says, at least current ones, the performance advantage isn't quite enough to be worth the extra trouble, that you can just throw a little more propellant at the problem with a chemical rocket and get very similar performance. I'm not going to get deeply into that today. Our premise here today is that chemical rockets are the way to go for the next step outward. What this session is going to be about is how to best get the ball rolling over the next decade or so with what we've pretty much got in hand in way of technologies and what's very near term. We're going to get to the point where my notes get really incoherent and chicken track. You'll forgive me the occasional pause while I try to figure out what on earth I meant and what I should be talking about next. It's been a little bit of a disorganized road trip, but I'm out of practice. At any rate, I'm going to do something that's, I'm told, a sign of maturity in the industry. I'm going to talk about cost. I'm going to talk about cost fairly extensively. As I said, if you don't know how much, you don't know when it's going to fly and how much it's going to cost to fly it, it's pretty hard to plan anything on the far end of it. Our first really big space project, Apollo, is not really the example we want to follow for reasons I'll get into. It was spectacular. It was an astonishing achievement. But in current year dollars, the Apollo program cost about $150 billion to put roughly 100,000 pounds mass total on the moon over a total of 6 missions. That works out to about $1.5 million per pound landed, and leaving out the factor of what's brought back and so on. I won't get into the overall value proposition. At the time, to solve the problem it was intended to solve, it was a good investment. But long term, there have been some interesting effects from that. Talk a little bit about why it cost so much. They were pretty much starting from a dead stop. We had a limited amount of rocketry experience going into Apollo. We didn't know how to do a lot of the things we needed to do. It suddenly became an urgent priority, urgent national priority when it got dragged into the Cold War. At which point they were willing to throw essentially unlimited resources at the problem. So they ended up solving the problem in an old-fashioned way. They invaded space, essentially similar to how they did the D-Day invasion. They broke the problem down into a huge number of very simple separate components, and then they overwhelmed each component with resources. They took every unknown problem and basically paid very skilled people to look at 2 or 3 different ways of solving that problem and get quick answers, pick the most promising one, adopt that, go forward with it. Something like 600,000 highly skilled people working on Apollo, something like 200,000 of them in the government. You can imagine the sort of payroll that would be involved on that these days. As I said, the project cost $150 billion overall. The other reason it cost so much to produce a relatively small amount of landed mass was that they dealt with the limitations of chemical rockets the old-fashioned way by stacking smaller rockets on bigger ones and throwing away the bigger ones to get the smaller ones further out and closer to the target and then light them up and go on. If you look at an Apollo-Saturn stack, there are actually 6 separate rocket stages involved. 4 involved in getting to lunar orbit and back, 2 involved in getting down to the surface and back. All 6 of them get thrown away at the end, by the end of the thing. That's neither the project management approach nor the stacking up rockets and throwing it away approach was economically sustainable in the long run. It's not really a surprise that we stopped doing Apollo in hindsight. Something interesting happened. Interesting and logical at the time, which is that when Apollo wound down, all the enthusiasts involved couldn't quite believe that we'd ever stop doing this neat stuff just because it cost a bit more than the Congress was willing to pay for. So NASA did something that seemed very logical at the time, and you'll read about it in histories. They quote, kept the team together. They basically maintained the core of the team that could do these complex procedures and kept them on the payroll and kept looking for projects at a much lower budget level that they could use to keep it exercised and go on doing space. Essentially, what they did with that massively parallel, cost is no object, do it quick, do 1,000 different things quickly approach at Apollo, is when they no longer had that kind of money to throw at it, they threw time at it instead. Which is basically why NASA projects currently in the evolved descendant of those procedures tend to grind on for a very long time while they deal with all the details. They can't do it in parallel anymore. They don't have the money. Let me see how I'm doing for time here. Okay, I'm going on way too long on the early stuff in the talk. Long story short, 50 years later, we've come up with a better way, or revived a better way. Fast turnaround, build, fly, build, learn by doing development. Took aviation from biplanes to Mach 3 jets in 2 generations. Took rockets from amateur curiosities to orbit in 1. Paradoxically, accepting more risk in some steps of the development process leads to far less cost, time, and risk overall. Combined with streamlined commercial project management and modern materials and electronics, the result has been dramatic. I think I mentioned that the cost of getting to low Earth orbit with increasingly reusable rockets has dropped 5 to 10-fold, and it's already down near 1,000 a pound and dropping further. We've got a growing and vigorous commercial industry doing that. Nobody here is surprised by any of that. As I said, it's going on in Seattle and Hawthorne, and at this point, dozens of other places around the world. You can't turn around without tripping over a startup rocket company. It's great. So what does this have to do with us here? The cost of getting from low orbit to the moon's surface and back with space-to-space round-trip reusable rockets, done this new old way. works out to very roughly 10 times the cost of getting to low orbit. It's not a fixed multiplier, and it varies a bit depending on your assumptions, and who you're arguing with and how they go about it, but that's the ballpark. That's in the ballpark of 10,000 a pound delivered to the moon, as opposed to the 1.5 million a pound from Apollo. 10,000 a pound seems very expensive and isn't cheap, but it's enough cheaper than the old way of doing things. We can start seriously looking at things like doing the prospecting we need on the moon to figure out where the resources are and how to extract them, and move on from there. Also, the costs to getting to the moon will continue to drop from where they will be soon, as cost to low Earth orbit drops further, as in-space rocket reusability improves. I didn't mention that getting it down to 10K pounds does involve reusing the rockets that go there and bring stuff back, and especially as lunar propellant becomes available to feed into the system. It's getting down to where we can actually start doing these things. We can get to somewhere halfway affordably where there's materials. We can start getting the costs down. We can start actually exercising all of these projects. We can start practicing off-planet construction. We can start feeding off-planet materials into it, or at least experimenting with the techniques for it. I've got a quick policy aside. I'm going to venture into the edges of politics. This addresses some things that Justin Carl was talking about also. NASA is evolving, slowly and painfully and not always evenly, but they are evolving. Commercial cargo before it, commercial crew is a prime example of the new hybrid approach, where they bring the commercial companies with the commercial approach in and blend it in with theirs. It hasn't always been a smooth process. It's evolving, but essentially in the future, some hybrid behind the Apollo descendant system at NASA and the new old commercial approaches is not just inevitable, it's current government policy. Well, it's probably inevitable, and it is current government policy. Policies change, but this one should be encouraged to continue no matter what. My take on all of that is that the more NASA could bring itself to embrace the new commercial approach, the farther it will be able to go on the substantial but far from unlimited amount of money NASA has to work with. See how I'm doing for time here. Ooh, we're running way into my allocation. I better get going. Don't want to cut into lunch. Okay. We're on the verge of being ready to do it. Now I'm going to try something really ambitious. How many people here are seriously familiar with the rocket equation, can do what George Sowers was talking about, casually invert it, ring the changes on it, and so on? A surprising plurality. How many, the rest of us have heard about it endlessly and our eyes glaze over a bit because there's math with funny symbols involved, and we've never really had the time to look into it. We probably could handle it. I'm going to try to explain the essential consequences of the rocket equation without doing any math you need to take your boots off for. In fact, I intend to take a cowboy's approach to rocketry. And with that, our next slide, a cowboy propulsion device, an Old West six-shooter. It's sort of an unusual six-shooter. For the sake of keeping the math simple, it weighs 1 unit of mass. We'll call it a pound. It's just a matter of convenience. It contains 6 bullets that each weigh a pound. So the total mass of the system is 7 pounds. And it fires them at 1 unit of velocity. We'll call it a kilometer of a second. Again, just for convenience sake. Anybody who actually knows guns knows this is a very unusually high performance gun, but that's beside the point. It's an example. Quick digression. Quick digression. The only way we know to move forward is to push something else backwards. The lunchtime session yesterday, things look promising, but anything that doesn't depend on mass times velocity equals mass times velocity, whichever law of motion it is still pretty hypothetical at this point. You have to push stuff backwards to move forward. The rockets are the best way we know to do that. A quick example, if you weigh 99 pounds and have a 1 pound rock in your hand and throw it at 100 feet per second, which actually is within the realm of the physically practical, Standing here on Earth, essentially nothing will happen. The rock will go away from you at 100 feet per second until it hits the ground. It slows down. That's because you're standing braced against the Earth, which is an essentially infinite mass. If you're in space through that 1-pound rock at 100 feet per second, something interesting would happen. The rock would actually go away from the original system point of origin at 99 feet per second, and you at 99 pounds would go away at 1 foot per second in the opposite direction. MV equals MV, 1 pound times 99 feet per second, 99 pound times 1 feet per second, everything cancels out. You've just built a primitive rocket. Our 6-shooter here is a little higher performance. 6/7 of the original system mass is what we call propellant. It's the stuff that goes backwards so you can go forward. 1/7 of it is the actual vehicle mass, the mythical self-firing gun that's sitting there in space. And again, there's no cowboy actually holding it, and he's not braced against the Earth. It's floating in space. So both, when you fire it, the gun will move one direction, the bullet will move the other. Our first hypothetical case, and I can't help it, this was going through my head. It's always struck me as a great line, an old rock and roll song, fire all of your guns at once and explode into space, all very exciting and adventurous. It turns out it's a terrible method to produce propulsion. If you do that, it works out, assuming you could fire all the bullets at once. You've got a system mass of 7, bullet velocity of 1. You've got 6/7 of it going, 6/7 of the mass going off at 1/7 of the velocity, propellant. You've got 1/7 of the mass, the gun, going off at 6/7 of the velocity. So your reaction mass, your propellant is going off at most of a kilometer a second, and you're going at a small part of a kilometer a second, and you're going off at about 0.86 kilometer a second, which is not very efficient. You might think you'd be going a lot faster than that, but it doesn't work out that way. It turns out that it's much more efficient to fire them one at a time. What happens then, you fire your first bullet. That's 1/7 of your mass going off, 6/7 of it being propelled. You end up being propelled at 1/7 of a kilometer a second. You fire your second bullet, your system mass is only 6 at that point. So you add 1/6 of a kilometer a second. You fire your third bullet, you add system mass is 5 at the start, you add 1/5 of a kilometer a second. By the time you get down to the last bullet, that's 1-pound bullet, 1-pound gun, that's half your mass. They each receded a half kilometer a second from each other. The net result adds up to about 1.59 kilometers a second. You're getting much more propulsion out of those bullets. It seems like we're headed in the right direction, and it seems like those numbers almost seem to indicate there might be a curve involved, and there is. If you plot never mind. I roughed these things out in pen and ink, and didn't have time to convert it to anything nicer. I ended up throwing it on the scanner before I dashed out the door to the airport. So my hand-drawn charts. You've got shots in sequence across the bottom. You've got velocity, the resulting velocity of the gun across the left-hand side. You end up in a curve up to about 1.59 kilometers per second as you fire the gun. It's looking almost rocket-like. In fact, what's happening is that each time you fire a shot, it's adding velocity to all the subsequent shots, all the subsequent propellant. The whole system is accelerating, so each subsequent shot can build on that with less system mass because you've gotten some of the system mass out of the way by firing it. The logical progression is if you were to somehow fire the propellant out continuously, you would probably get better performance. And in fact, you add that second curve there, and next to your very high performance gun, you've got a very low performance rocket. And the infamous rocket equation, which I won't bother you with more. Delta V is velocity change, natural logarithm, ln key on your calculator if you two want to play a rocket scientist on the internet. Mass ratio. And mass ratio is interesting. We're going to pay some attention to mass ratio. You take this gun with 6 bullets, each unit mass same as the gun, that's total mass of 7. That's your system starting mass before you start firing any propellant. Your system ending mass after you fired is 1, the gun. So that's a 7-to-1 ratio. That's your mass ratio. That's useful to know for rockets. How much does it weigh before you start firing engine? How much does it mass after you've fired the engine? That's a critical factor. You take the natural logarithm of that and multiply the exhaust velocity. Result is faster exhaust velocity proportionately gives you a faster rocket. More mass gives you diminishing returns faster rocket. Because the final key thing on this chart, if you were to add you do some clever gunsmithing and add a 7th shot, it would show up on the left-hand side at the start. And it would have to propel all the subsequent shots that are still sitting there in the gun. And you would only get, 1/8 of the unit velocity out of it. An additional shot, you'd only get 1/9, an additional 1/10. The result is that the actual velocity versus mass ratio curve for a more or less generic hydrogen-oxygen rocket looks like that. You've got mass ratio along the bottom, 5, 10, 15 times the final mass in starting 2025. And you've got your velocity change on the left. This is for hydrogen, oxygen, exhaust velocity about 4.5 kilometers a second. Essentially, at about mass ratio 3, you get about the equivalent of your exhaust velocity. At about mass ratio 7, you get roughly twice. At a mass ratio in the mid-20s, you get 3 times it. And your mass ratio has to go up near 50 before you get 4 times it, at which point you're talking a rocket that is extremely fragile, basically all the durability of a water balloon. Not good for reusability. The thing about this chart, and I wish I had a laser pointer, but the lower left-hand corner of it, between about 10 on velocity and about 10 on mass ratio, is where you can build practical rockets that are robust enough to be reused and still have a reasonable payload. So the rest of this talk is going to be discussing how we can get around in cislunar space using only reusable rockets that operate down in that lower left corner of the region, that essentially can get there and back within that 10 kilometers a second or so, within which you can build a reasonable rocket that's reasonably rugged and reasonably reusable. Speaking of cislunar space, a simplified version of actually, let me back off a second. Everybody here has been talking kilometers a second at you, who's talked, getting anywhere in space. How many of you have a good handle on how fast a kilometer a second is? A short version, it's about 2,200 miles an hour. It's about as fast as an old SR-71 Blackbird reconnaissance jet. You're talking Mach 3 plus, coast to coast in a little over an hour. 4 to 5 times as fast as the jet airliner that probably brought most of you here. It's pretty fast. But meanwhile, it's basically the opening bid in getting around the Earth-Moon system and beyond. Most of the velocity changes you need to get anywhere interesting beyond low orbit are in the low to mid single digits kilometers a second. You need a lot of fairly efficient propulsion to get there. You need good rockets. This is a quick chart of getting from, not to scale, bad artwork, but that's okay. If you're going to start in low orbit and you want to get into what they call TLI, another 3-letter acronym, TLI, translunar injection, that's basically enough velocity to get from low orbit up over the gravitational hill to where you're coasting downhill again towards the moon. It's about 3 and a fraction kilometers a second, which is fairly substantial. You then need to slow down again at the moon so you don't overshoot. You need another kilometer a second of braking down the far side of the hill to get into low lunar orbit. You then need a bit over 1.5 kilometers a second to actually land on the moon. One way to get back and forth to the moon cheaply is to simply get to low orbit and build a very high performance reusable rocket that can carry a lot of propellant that can make it all the way from low orbit to a lunar surface landing and then back to Earth. That's what, 3.1, 4.1, about 5.8, so about 11.5 kilometers a second if you're going to rocket brake back into low orbit. You can cheat a bit on that. You can cut it to about 10 kilometers a second if you aero brake. You can't aero brake all the way back into orbit currently. It's not state of the art. Or you can cut it to about 8.5 if you re-enter to Earth. But you need a lot of velocity change in a rocket. If you're going to do that, you need large amounts of propellant. You need landing gear for the moon. You need variable thrust motors for the moon. You need aero braking and re-entry provisions for coming back to Earth. Basically, it helps if you build a honking big rocket. It's easier to fit all those things into it with a light enough mass. No surprise is the approach they're taking down the road in Hawthorne to get there and back. They're doing it for their own reasons. They want to. Elon doesn't tell me why he's doing things either, so anything I say here is my best guess based on the available evidence. But I think the reason they're making Starship so big is to get some economies of scale and fitting all those systems into it to be able to do all those versatile things. The reason they're making it so versatile is simply because they've only got a certain amount of engineering bandwidth before their engineers start exploding in puffs of smoke. They work people pretty hard, and God bless them, they're doing extraordinary things. At any rate, this is one approach to getting to the moon. You build Starship, you refuel it in low Earth orbit. By the way, it takes between 10 and 12 additional Starship tanker flights to refuel it, enough to go to the moon and back. It's not just, that point tends to get missed a lot. You're basically talking a dozen Starship flights. But at that point, assuming they can hit their performance, assuming they can make everything as light and rugged enough as they're trying to, you can carry a very substantial payload, land it on the moon, leave it there, come back, re-enter to Earth, and repeat the whole process again at a price, oddly enough, in mid to high thousands of dollars per pound payload delivered, depending on what the cost of each of those Starship flights is. Again, they're not sharing their information. That's what SpaceX is doing. I'm giving it equal time. They're too busy learning aerospace grade stainless steel welding to come here today and tell us about it. So that's my best guess as to the approach they're taking. It's a valid approach. It'll be useful. I hope it'll be useful. I hope it works well. The more people playing in this, the better. The approach we're going to be talking about today involves that Dallas and John are going to be talking about today involves breaking the trip down into two parts at a logical waypoint. You could even call it a gateway, someplace you can stop, change trains, and continue the journey. The reason for that is then you can specialize the two vehicles. One handles between Earth and the waypoint and is able to aero brake. Other handles between the waypoint and the moon and is able to land. They need different hardware with different weights. You can build them lighter and more rugged, also because they don't have to carry nearly as much propellant because they only each have to make half of the trip. Fortunately, there's a whole series of natural waypoints at what you might call the gravitational hilltop, multiple hilltops between the Earth and Moon. If you think of it in terms of, you get your 3 kilometers a second velocity coming out of low orbit, you coast up a hill till you get to the top and just barely roll over, like getting up a lot of speed on a bicycle to get up a hill. With a little extra effort, you can stop at the top of the hill. You can actually park things at the top of the hill and more or less have them stay there without a lot of work. You can then give them a fairly small goose, coast downhill to Luna, brake, land. It's a more or less natural break point for a voyage, and as I said, it lets you break it down into two parts and make the rockets. It's a more complex system, but there's more margin and more ruggedness in it. So it's debatable which is going to work out best in the long run. We're going to be talking mainly about the latter approach today. The last bit of this talk is there's actually multiple hilltops up there. The most massively not to scale drawing I've done yet. The infamous Lagrangian points, balance points between Earth's and Moon's gravities. There's more than one. The most interesting one is Lagrangian point 1 that's actually between the Earth and the Moon. Some of us are advocates of it. It has advantages. It's in a fixed location, and you've got a fixed schedule between Earth and Moon and between Earth and it and Moon and it. It doesn't change over time. The energy costs to stop there are a little higher, maybe on the order of 3/4 of a kilometer a second. The other one that's of immediate interest is something obscure called a near rectilinear halo orbit, which is that oval I attempted to draw that dips close to one of the moon's poles, then goes way high in the other direction. It's not technically a lunar orbit. It's actually an orbit between the balance point between the moon's gravity and either EML1 or EML2, and the math is complicated, and I won't try to get into it. A cowboy could not do it without taking his boots off. We're not going to talk about it here. The interesting thing about NRHO is it's a little easier to stop in if you do a tricky maneuver where you fly close by the moon, do one burn, and then do another burn. Finally, when you get to NRHO, you can get in and out of it for about a little less than half a kilometer a second. The reason this is interesting to NASA is because aerospace projects have weight growth. Orion has weight growth. Orion, as it matches to its propulsion module right now, has maybe 1,200 meters per second velocity change once the SLS has put it into translunar injection, which is not really enough to stop at most of the gravitational hilltops and then get out of them again and have a reasonable amount of maneuvering margin for unexpected contingencies. About 450 meters a second each direction leaves you with about 300 meters for contingencies in and out of NRHO. Orion can get to NRHO, so that's where they want to put Gateway. It makes sense. It's not as good as EML1 for regular schedule. They mentioned 12 hours back and forth to the moon, but that's only at certain points in that orbit. Other points take longer or cost more energy. It's sort of a fixed schedule thing. But the real answer, it's okay wherever you want to put Gateway, because whatever you invest in it, you can get between those various hilltop points for on the rough order of 100 meters per second in a little bit of time. You set up something in NRHO, you can move it to L1 later if that turns out to be a more useful spot, or wherever else might be a more useful spot. I have gone way over my time. I'm going to see if there's anything else essential I wanted to say. Not really. John, are you still awake?
I'm here.
All right. I will turn it over to John Schilling now, who will actually tell you stuff you don't already know, most of you. Those of you who already know most of this stuff, thank you for bearing with me. Those of you who, like me, are sort of amateurs at this, I hope some of it was useful. John, take it away. I'll have your slides up and get out of your way in a second. It will be several seconds. I just hit the power button instead of the escape button. It's been one of those road trips. John, I don't know, do you have anything to say while you wait 2 minutes for your first slide?
Oh, well, I might as well just start out. The topic of the first section of this talk, I had broken it up into two in hopes that John Goff would be talking depots in between. But I'm going to talk about what we can do with launch vehicles that exist or are in a fairly advanced state of development. A couple of times yesterday we heard, assuming Starship does everything that it's been promising, and I can go back 40 years and hear talks very much like this saying, assuming the shuttle exists and does everything it's promising, assuming Delta Clipper exists and does everything that it's promising, assuming X-33 comes through with everything it's promising. Let's not wait for the promises to be fulfilled. Let's be a little bit more pragmatic about what we can do with what we got right now. And
no, it'll be another minute or two.
Okay.
It's an ancient, slow machine.
Okay, so I think I can do my first slide from memory. My criteria for right now is something that is funded for development through first orbital flight with reasonably high confidence by 2024, which means that they have to be at least promising by 2021. It has to be something that's at least semi-reusable, otherwise we're never going to get the cost figures that we're looking for. And I'm hoping for things that are traceable to fully reusable systems. It has to be delivering at least 5 tons to low Earth orbit, because that's the smallest size chunk you can really break interesting logistics infrastructure development payloads into. small satellites is an entirely different field that's interesting in its own way, but you're not going to be building, any of the space habitats we saw yesterday, 500 pounds at a time.
Okay, there's your first slide.
There's my first slide.
I will get out of your way now.
All right. So, 4 candidates come through out of this. 2 from SpaceX that are already flying. United Launch Alliance and Blue Origin are in a fairly advanced stage of development. SpaceX, Starship, Super Heavy, BFR, whichever they're calling it this month, they don't really have enough technical detail for me to assess it yet. And there are still some credibility problems given that the funding is essentially entirely out of Elon's pocket and maybe a few of his fellow investors. And the market at this point is entirely out of Elon's pocket and a few of his investors. Nobody's promised to buy any of these yet. So that's a fairly big single point failure that takes away a bit of credibility. So like I said, I'm trying to figure out what we can do if that doesn't come through. And then NASA's SLS is just too big, too expensive, and not at all reusable in any incarnation. I assume most people here are sufficiently familiar with the Falcon that I'm not going to describe how it works in detail. The point is it's a medium launch vehicle. It takes a little over 15 tons or 16 tons to LEO, about 3 tons to GEO, which gives you the communications satellite market, which is what is paying Elon's bills while he's working on more advanced systems. So that works out very well for that market. The latest version is nominally capable of 100 flights. It's so far demonstrated only 4, but it's working well. So, I will consider a couple of variants on this, in particular, fully reusable variants. Falcon Heavy, same thing on steroids. 3 first stage cores instead of just 1. 43 tons to the low Earth orbit that I'm considering here, 10 tons to GEO. 14-ish tons to the moon, which is pretty interesting for reasons we'll get into. And I need to update this slide because it's done 3 flights now, all of which have used some hardware that was reused from earlier Falcon 9 flights. I don't think they've done a full Falcon Heavy to Falcon Heavy reuse yet, but it'll be coming. Again, we'll consider some variants. The United Launch Alliance Vulcan does not exist yet. This is going to be the replacement for the new, or for the old Atlas and Delta series of rockets, which have their issues. Supposedly going to be cheaper, better, higher performance. This one is fully funded because the government is absolutely counting on it for all their national security payloads. This is going to happen. It has, in its initial format, nothing of interest to us because it's not reusable. But they are proposing to recover the first stage propulsion and probably avionics module, the expensive, hard-to-build parts, by just separating those off from the sheet metal propellant tanks and parachuting those back. Not quite as neat an approach as SpaceX's, but it'll do. It also has an upper stage, which is designed with the idea that it might turn into a reusable space tug on orbit. That's not going to happen in the first generation, first variant of this vehicle, but ULA has thought ahead in how to do that, so that's worth considering. And finally, from right up here in the Seattle area, the Blue Origin New Glenn, which is basically just Jeff Bezos' answer to the Falcon Heavy. Locks methane rather than locks kerosene propellant for the first stage, locks hydrogen upper stage. Roughly similar performance. Again, first stage reusable, second stage not so much. This was originally conceived of as a system with 2 stages for low orbit missions and 3 stages for missions beyond that. They've apparently suspended development of the 3rd stage because they don't need that. For the things that we're talking about, a 3rd stage will be necessary. Fortunately, even if they don't develop a 3rd stage, the 3rd stage from the Vulcan vehicle, the ACES stage that we just talked about, would slide neatly into that spot up there. So I'll talk about that as a possible variant. I mentioned we would really like fully reusable systems. SpaceX has from time to time talked about a fully reusable Falcon, about recovering and reusing the upper stage. This is the most recent concept I could find for that. It's not currently active, but because they keep talking about it and not talking about it. My assumption is that if the Starship does not work out as well as hoped, they'll go back to talking about reusable Falcons. And I've made sort of my best guess as to what a reusable Falcon would look like if they bring it back again. You can see some assumptions on the side that I don't need to go into. The point is, you lose about half your payload if you make a Falcon recoverable because you have to carry a lot of stuff into orbit, heat shielding, additional propulsion, landing gear, and so forth to get that second stage back. But if you lose half your payload and you're talking about an 80 to 90% cost reduction because you're not throwing anything away, that's probably a net win. But the performance cost puts some constraints on you that I'll talk about in just a second. Yeah, this is the upper stage for the Vulcan. Again, well, if any of you are familiar with the old Centaur upper stage that's been flying pretty much continuously for 50 years, this is a Centaur on steroids, LOX hydrogen, 4 engines, high mass ratio. But they've done some very nice systems integration to improve endurance, complex mission capability. Like I say, turn it into a reusable space tug. And then Maston Space Systems has also looked into how to turn this into a lunar lander. Add all these up, this is what we get to low Earth orbit. A number of launchers that are delivering 15 to 20 tons to low Earth orbit. There's a lot of particularly national security and some manned space payloads that are in that range. Then the Falcon Heavy and the New Glenn are up around 40 tons. The fully reusable Falcon 9 is only at 7 tons, which is kind of marginal for what we're talking about here, but it's in the range of interest. A fully reusable Falcon Heavy could still put almost 28 tons into low Earth orbit, and that's very interesting. Fully reusable New Glenn would be 17.5 tons. And this is for, I should point out, an operationally useful low Earth orbit, 400 kilometers at 30 degrees inclination. You often see numbers quoted for much lower orbits that are not stable long enough to be useful. So that's why my numbers come out a little bit lower than what you might see in some references. If we're going to cislunar space, to what Henry called the top of the hill, and as he said, pretty much all hilltop points are equivalent, but I did the near rectilinear halo orbit as my baseline. The Falcon 9s can barely get there. You might get some supply shipments from that, but not much. The Vulcan, similar. This is really where you're talking for the heavier vehicles, the Falcon Heavy and the New Glenn, to be interesting. They can deliver 10 to 15 tons. That's enough to do serious manned space flight or logistics development. And with the exception of the Falcon Heavy, none of the plausible reusable configurations can reach there. As Henry pointed out, if you build something the size of a Starship, truly gargantuan, exploiting the economies of scale, it's not unreasonable to talk about going to the moon and back with a single-stage reusable vehicle. But doing it with vehicles that we currently have or in the pipeline, the Falcon Heavy is the only one that can even barely make it, and not with a really useful capability.
Are those TLI or capture?
I did do full capture for these. And in the case of the Falcon 9, which has no capability of doing its own capture burn, I threw in the mass penalty for a small biprop RCS.
Another question, is standard booster recovery and reuse, but
Yeah.
first, second stage, and then full reuse includes the second stage being recovered and reused?
Right, yeah. Yeah, I did not do any math for anything that doesn't at least recover the first stage, because that's just not going to be cost effective. So the key points on this, we can deliver lots of payload to low Earth orbit with these in usefully sized chunks. If a 40-ton chunk of payload to low Earth orbit is not good enough for you, you're not trying. You can assemble anything from 40-ton chunks. You assembled this building and things that came here in trucks and railroad boxcars. Going beyond low Earth orbit, even to something as close as GEO, you lose about 80% of your payload. That gets kind of marginal. And it turns out that there's not much difference between going to GEO and going all the way to, say, trans-Mars injection. I have charts for all of those in my backup. They all look fairly similar. If you're going fully reusable, you can do that as far as low Earth orbit, and it costs you half your payload, which still leaves you reasonable capability for the heavier vehicles. Going beyond low Earth orbit with a fully reusable vehicle, That just takes you too far up the exponential rocket equation that Henry just showed you. You're well out of that 10 kilometer per second box. Not really practical. Therefore, in order to do anything beyond low Earth orbit at a reasonable price, I think we do need a logistics base in low Earth orbit, simply so that we can do the mode shifting between the high-performance, reusable space launch vehicles that will carry cargoes from Earth to orbit and down and be very specialized in doing just that, and the vehicles that Henry was talking about that are more optimized for in-space transportation. A few other minor points. Like I say, the New Glenn needs an upper stage to be doing anything beyond Earth orbit, and the folks at United Launch Alliance have actually built, or designed, not yet built, one that would fit fairly nicely. So that is what I have to say about launch vehicles.
Well, let me see if I can get your next slide set up without hitting the off switch.
Okay. I'm going to talk about them briefly. As I said, that was John Goff's talk. Key point about a depot is that it needs to be more than just a propellant depot. That's something that people talk about quite frequently. There are gains to be had just by putting, a fuel servicing station in, say, low Earth orbit or in cislunar space, where you could stop off and fill your tanks. But when you're talking about robust, reusable launch vehicles, you're not going to fly 100 times with nothing but topping off your tanks. You can do that with a car. You can maybe do that with an airplane. You are not going to be able to do that with a high-performance rocket. And doing it with an airplane means doing it with a very low-performance airplane at limited margins and limited safety margins. You really need, after no more than 5 or 10 flights with a rocket, to have either a person or a very capable robot go over that and fix all the things that are broken or marginal. Tighten up leaky valves, maybe reapply some coatings that have worn thin. A lot of little stuff like that needs to be taken care of. At the other extreme, a depot is not necessarily a space station, because the word station attracts a lot of people who will get in the way of the logistics operations that you're trying to do. In particular, if you call something a space station, people expect there to be people on it all the time doing stuff. If you've only got logistics work to keep them occupied a few months a year, as we heard for the Gateway station yesterday, and somebody insists on putting people on that space station 24/7, 365, because it's a space station, and that's what we do with space stations, they're going to be scientists, they're going to do science experiments, they're going to start whining about how your refueling rockets is ruining their microgravity. You really want something that is narrowly focused on logistics alone. It might have a science platform a few kilometers off that it supports, and you want something that is optionally manned. Some things probably will require human touch labor in servicing spacecraft for the foreseeable future. You want that capability, but you don't necessarily need people living there 365 days a year. So start with a propellant depot, because that gets you the near-term gains. Throw on docking ports where you can aggregate multiple vehicles and payloads, robot arm to assist you in doing that, and then build up what the aviation people call the maintenance, repair, and overhaul capability, including a Salyut level or Almaz or Space Hab level habitat where a few people can live and work for a few weeks at a time. Eventually, it will turn into a fully manned, full-time space station, but don't overdo that at the start.
John, I would note that Elon does have a customer for BSR who's helping pay for themselves.
I think I know who you're talking about, and I don't think it will anywhere close it for him.
No, it doesn't close it, but he does have a customer.
Okay, yeah, to be fair, one small customer in the grand scheme of things. So where am I? This is a slightly fancier version of the map that Henry showed. Basically, everywhere we're thinking about going in the near term, I've tried to do a 2D projection of delta V mapping, which doesn't work anymore for outer space than it does trying to print a globe in 2 dimensions mapping the Earth, but it's reasonably close. And the important thing is that right there in the middle are the 4 points marked in red, L1, L2, L5, and the NRHO orbit where NASA plans to put the Gateway Station. And there's a few others that belong in that same spot. Key takeaway is it is really one spot. It's the top of the hill, and it doesn't matter exactly where on the hill you park. And it's really kind of in the middle of all the interesting spots that we're thinking of going to. So it does make a good point for logistics space. The other good point for logistics space is low Earth orbit, the reason being that on the scale of this drawing, the actual Earth is somewhere in the basement. Just getting to low Earth orbit takes every bit of capability that Henry pointed to as the 10 kilometer per second, mass ratio 10, limit of the box, saying we can do this with just one depot, we can go straight to the gateway and do everything from there, straight to L1 and do everything from there. That's kind of a step too far. You really need the mode shift and the stopping point in low Earth orbit. So turn that into a list of missions that I've considered for here. All the places we're going to go to, we could go directly from Earth, or we could use one or both logistics bases to facilitate that. We already talked about, I forget the name of the man from NASA who was here mentioning the Gateway Station yesterday, but he went over this in some detail. I'm not going to repeat it. It has a lot of interesting capabilities. One thing it's missing in the short term is it does not have in its Mark I incarnation a propellant depot. But they've said some things that make me think that NASA is amenable to having a propellant depot added to the gateway as soon as anybody's in a position to use it. Henry talked about the near rectilinear lunar orbit. It's very convenient for NASA's plans for lunar expeditions. It's okay for pretty much any lunar expedition plan. You do have to sometimes wait a week or two to line things up. It's somewhat inconvenient if you're going to, say, Mars, but not to a level that would prohibit it from being used for a few early Mars missions. And if we decide to transition to a more Mars-focused or asteroid-focused policy, maybe the asteroids do turn out to be a better source of raw materials, then we just move the station, like Henry said, or build a new one. NASA, earlier this year, came out with a plan to use the Gateway Station to support lunar exploration with a combination of 3 vehicles. They put out a broad agency announcement saying we'd like people to start work on 1 or 2 of these. A lunar lander, an orbit transfer vehicle to push the lander around in cislunar space, and a refueling element, which is just a propellant tanker coming from Earth. All of these were sized not for SLS, but for Falcon Heavy, or possibly New Glenn. That's a good sign. It means that people other than NASA can use this architecture. One interesting thing about this is that while they specified 3 vehicles, the OTV and the tanker are pretty much the same vehicle. They both weigh about 15 tons, because that's what a Falcon can deliver. They're both mostly propellant tanks. They're both high performance or high capability autonomous deep space vehicles that can operate for a week or so, conduct docking rendezvous, some degree of propellant transfer. The only difference is that the OTV has to have a higher thrust engine, and the tanker has to have a more sophisticated propellant transfer capability, active rather than passive. There's no reason to design 2 completely different vehicles for that capability. You design one vehicle that can do both and maybe have a stripped down variant for missions that only require 1 set of capabilities. But start with the lander. This is a lander that meets NASA's requirements, and I've added 2 capabilities NASA didn't specifically ask for. Number 1, it fits inside a Falcon Heavy or Blue Origin fairing, which they did ask for, but it also unfolds so that it can wrap around any other payload that also fits inside a Blue Origin or Falcon Heavy fairing. Gives you a bit more capability. The other is that this one was designed to be reusable from the start. And this is just a very coarse concept level design, not a whole lot of detail going into this, but one element of this proposed architecture. The other is the OTV, which, as I said, doubles as a tanker. It can dock with and push around the lander. Also 15 tons, LOX hydrogen propulsion, relatively limited capability in terms of thrust, but it'll do the job, and it does have the propellant transfer capability. In particular, what I added on this one that they didn't specifically ask for, it can do propellant transfer while the lander engines are burning at the rate needed to fill the lander engines. So you can run the lander using only the propellant from the tanker. And in this orientation, that's a straight gravity feed, which simplifies things. Couple of variants. You might build a cheap tanker-only variant for some early missions, and you will eventually build a version that does have its own high-thrust propulsion and limited aerobraking capability. I'll explain why. So, and a 4-ton drop tank module. NASA didn't ask for that, but that'll also be useful. Again, this is the ULA's version of the same thing. It's basically just proof that great minds work alike, because their version of a cislunar transportation system is very similar to the one that I just described. It's just that everything is 5 times larger because it's sized to meet their launch capability to low Earth orbit rather than Falcon Heavy's launch capability to cislunar space. Slightly more efficient in the long run, but it's far too heavy for anything NASA's planning to do at Gateway in the short term. So if we're hoping to cadge off NASA's budget or guaranteed market support to get something in flight early, this is overkill. Long term, it's useful competition, somewhat more efficient, better for the larger payloads. What can we do with all this? Well, we can do what NASA asked. We can launch all 3 elements to the Gateway station, combine them, land the payload, abandon the lander in place on the lunar surface, fly the space tug back to the Gateway and say, yay, we reused something. Gets you about 12 tons to the lunar surface. We can even do that without the Gateway, assuming you're willing to trust autonomous rendezvous and navigation in cislunar space. A little bit higher risk, a little bit higher performance because we don't have to reserve propellant to recover the space tug, but it means we're throwing away the space tug. And if you're sick and tired of people whining about the fact that it's been 50 years since Apollo, why can't we go back to the moon? We can go back to the moon. We can do Apollo with 2 Falcon Heavies. Maybe there's demand for that. Maybe we are tired of waiting. 1 Falcon Heavy or 1 New Glenn possibly delivering an evolved Dragon 2 and a custom-built manned lunar ascent stage weighing about 6 tons, a fully fueled lander. They rendezvous. In this case, you have people to help with that. You land the lander, leaving somebody to keep the Dragon operational, obviously. 2 or 3 people on the lunar surface do what they're going to do, and then that 6-ton ascent stage should have the performance to go back to what would be the Gateway orbit, rendezvous with the evolved Dragon, return to the lunar surface or to the Earth surface. So if NASA falls down on building the Gateway station, we can still do some preliminary lunar exploration with just these vehicle elements. But what we're really interested in is serious lunar surface operations, either for their own purposes, because we like the lunar surface as a destination, or because we want to strip mine it for stuff to use in cislunar space. Either works. To do that, we need to stop throwing away landers every time. You can use the same architecture, make the lander reusable. It was designed to meet NASA's requirements for an expendable lander. But if you're clever, you take the lander, the payload, the OTV into lunar orbit, do the start of your deorbit burn, about 350 meters per second, using propellant from the OTV while they're attached. The lander detaches. It's got a head start on its trip to the lunar surface. It can land and still have useful propellant remaining. The OTV is at this point on a suborbital trajectory that would crash into the lunar surface in about 40 minutes, but it's got propellant. It can recircularize back into low lunar orbit. When you've deposited your payload, you can bring that lander with its remaining fuel back up to low lunar orbit, dock with the tug, bring the whole stack back to the Gateway station. You've expended no hardware, dropped 12 tons of payload to the lunar surface, eventually 14 when we have surveyed landing sites and don't have to have quite as much propellant reserves. You can also do crew rotations and other surface returns missions with somewhat smaller payloads. This requires that payloads and propellant keep showing up at the Gateway station. We can use the same OTVs in a 2-tug configuration to deliver up to 12 tons of payload or 9 tons of propellant to the Gateway station and return the OTVs to low Earth orbit. This does require that we have a logistics base in low Earth orbit to restack everything, refuel everything for each trip. But now we have an architecture where we can get payload from the Earth's surface all the way to the Gateway or any other cislunar location, L1, L5, whatever, without throwing away any hardware, because you can use a fully reusable low launch vehicle to low Earth orbit. You can use 2 fully reusable tugs stacked to deliver payload to the Gateway, return the tugs to Earth, or to low Earth orbit. You'd never want to actually land them on the Earth. Now, why were we building things on the lunar surface when everybody from O'Neill's day to the present knows that L5 or something along those lines is the way to go? Well, aside from the fact that not everybody agrees with O'Neill, even O'Neill agrees, the moon is where you get your stuff. Maybe near Earth asteroids, but we'll start with the moon. And the first stuff we're getting from the moon is probably rocket fuel. You've got a base on the moon that's producing rocket fuel. Now the lunar surface is where you base your lander. Gateway is where you base your tug. When you have a payload to the lunar surface, the tug takes the payload down to low lunar orbit. The lander, fully fueled with local resources, ascends to low lunar orbit. They swap the payload out. The lander brings the payload down to the moon. The tug goes back to low Earth, or to Gateway orbit. You're not carrying quite as much payload this way, but 9 tons is still good enough. And you're only using 3 tons of Earth-delivered payload. Until you realize that you can use the same architecture to start ferrying payload, or start ferrying propellant up from the moon to the Gateway. 2 landers with auxiliary tanks meet 1 tug in low lunar orbit, deliver an almost fully fueled tug, in this case tanker, to the Gateway station where it offloads propellant. And at that point, you can even start using your Gateway station to deliver propellant, lunar sourced, to low Earth orbit, just a single round trip with a tug and an extra tank. And finally, you can use this architecture to support exploration of Mars, asteroids, even infrastructure development in geostationary orbit, if that's still a thing. It's a fairly complex mission profile because the lunar rectilinear halo orbit is very inconveniently oriented. You have to do a series of deep space maneuvers to reorient. You then drop into a very low perigee pass at Earth. For fairly complex orbital mechanics reasons, it's most convenient to do your big departure burn to Mars as you're doing a high-speed pass low over the Earth. When you do that, you drop off the payload. Then the OTV does another series of complex deep space maneuvers to get back to Earth. This is actually more efficient than departing from Earth orbit using propellant sourced from the moon. I looked through both, and I haven't presented the alternate version here, but an OTV weighing 15 tons, 12 tons of that propellant can put 21 tons on a trajectory to Mars, up to 25 tons to some reasonably near-Earth objects. So just to summarize all of this, well, one way to summarize this is what I call the lunar water economy. Everything here has been done with LOX methane or LOX hydrogen rockets, which means our rocket fuel is basically water. And there's a point of sometimes contentious discussion about when do you turn the water into actual rocket fuel? Do you do all that on the lunar surface? Do you ship water around and then use solar power to turn it into hydrogen and oxygen where you're planning to use it? It doesn't really matter. You're shipping water whether you're shipping it in 1 component or 2. Right now, the only place you get water is on Earth, shipped at great expense to low Earth orbit. And with 1 kilogram of water in low Earth orbit, you can see you can get about 1/4 of that to geo or cislunar space. You can get 12% of that to the lunar surface. Eventually, we'll start getting water on the lunar surface, and then it starts looking almost precisely the opposite of that. 1 kilogram on Luna becomes a little over 1/4 kilogram in cislunar space, 12% in low Earth orbit. So For now, we have to follow the green path. As water on the moon becomes cheaper, as it becomes a simple matter of sending a command to the robot, shovel a bit more ice into the converter, we'll send robot parts later, then the blue path becomes more attractive. And the Cislunar base, which is sort of at the midpoint on both paths, becomes a very convenient aggregation site when you're building things, some of which have to come from the Earth and some components of which have to come from the moon. Presumably, that's what started looking appealing to O'Neill and his students 50 years ago. And just when we're building out that lunar infrastructure, as Henry said, right now, 119-ish tons launched from the Earth turns into 10 tons on the lunar surface. Actually, I'm going to digress a bit and explain the color code on this chart. You're not going to see cost numbers in here because this is way too preliminary in architecture design for me to believe any cost number I attach to it. It takes a lot of effort and a lot of luck to produce aerospace costing figures that aren't fantasy. But what I can say is there are 5 categories of mass. The most expensive is dry mass delivered on an expendable or semi-expendable launch vehicle. Because the dry mass is complex aerospace hardware, we're not sending sheet metal, we're sending complex machinery, and we're throwing away half a rocket every time we do it. Well, less than half by mass, but maybe half by cost. Dry mass with a fully reusable launch vehicle, your transport costs get cheaper, but it's still complex hardware that's being built in factories on Earth at thousands of dollars a kilogram just for the production. Next up is propellant, which at least on Earth is cheap, but you still have to worry about launch costs, which are expensive in a semi-reusable launch vehicle, somewhat cheaper, fully reusable, but still probably hundreds of dollars a kilogram. And then propellant on Luna right now is priceless, but we hope, as I said, eventually that you just tell the robot to shovel more ice into the converter. So you can sort of get an estimate of what costs might look like by looking at what fraction of the mass is in each of those categories. Right now, 100 plus tons of the more expensive mass categories to get 10 tons on the lunar surface. With just the Cislunar base as an aggregation site to support specialized landing vehicles rather than the less efficient direct launch systems, you can cut that in half, as I just sort of showed. LEO logistics bases also have the effect of reducing your launch requirements by half, and they facilitate using reusable rather than expendable launch vehicles, if you have them. You can combine Cislunar and lunar bases, Cislunar and lunar surface bases now give you the ability to use lunar propellants, which produce further reductions, and in the end state where you have all 3 capabilities, a LEO logistics base, a lunar logistics base, and a lunar surface propellant manufacturing facility, now it's 10 tons launched from the Earth's surface becomes 10 tons landed on the moon. You just need to produce 167 tons of propellant on the moon to make that happen. And this is the same chart for delivery to anywhere in cislunar space. The numbers are a little bit different, but the takeaway is the same. And I have charts for Mars, near-Earth asteroids, geostationary orbit. They all look fairly similar. So conclusions. Yeah, the NASA concept of building a gateway station in cislunar orbit, genuinely useful. And their architecture isn't as bad as I thought it might be when I first started looking into this. The orbit's okay. The base needs a propellant depot, but is otherwise okay. Doing this is essential to make use of lunar surface-derived materials, especially propellants. Going directly from the lunar surface to low Earth orbit with a tanker full of propellant is not going to work. You need this to make use of in situ resources. The logistics base in low Earth orbit is also useful, and in this case, its primary virtue is that it facilitates the use of fully reusable launch vehicles and fully reusable deep space transport architectures. If you have both of these in combination, you're getting a 4 to 5 times improvement in how much payload you can deliver to deep space locations, lunar surface, cislunar space, Mars, what have you. The ultimate goal is we want to launch only the people and the most sophisticated manufactured goods from Earth. Everything else comes from lunar or deep space sources, and all the shipping is done with lunar or deep space propellants. I would prefer to start with the low Earth orbit base and get fully reusable launch vehicles in operation with a useful destination, useful logistics base to deliver their payloads for further transshipment as soon as possible. If that's not going to happen, then the Cislunar station that NASA has proposed is also a pretty good starting point. And I think that's what I have for regular charts. So I think the plan is that Dallas is going to talk, and then we're going to have...
We have time for a couple of quick questions that are specific to this presentation. We are going to get, if we have time at the end, we're going to get everybody up there and take general questions. So now, 2 quick questions here. First come, first served.
A real quick one, why L5 but not L4?
No particular reason.
Sentiment.
Yeah.
That's what I figured.
They would be overlapping if I put them on the chart, and L5 got here first.
More substantive. All those numbers you showed for mass ratios to various locations for the water, was that assuming cryogenic propulsion to get everything everywhere? Didn't consider electric?
All the propulsion is LOX hydrogen. I did this assuming that we have low but not zero boil-off tankage for LOX hydrogen in space. It's a little bit easier if you're shipping bare water, but I didn't run a separate set of numbers for those.
But no electric propulsion?
No electric propulsion.
Because that would change things.
Yeah, that would change for the LEO to cislunar capability. Electric propulsion would also be beneficial, and I didn't include that here.
Well, thank you, John Schilling. You'll have an opportunity to ask him a few more questions at the end. In the meantime, I'm going to get Dallas's slides up here. Hopefully, we're going to get Dallas up here. The question that came up a number of times yesterday was, how do you bootstrap economically from where we are now into one of these systems in space? And I believe Dallas is going to address that question, among other things here. I'll leave him to explain the details to you.
First of all, everybody stand up. Stand up. Your bum's probably getting tired. Stretch out, relax. Get the blood flowing. Excellent. Okay. Now that we've reached for the sky, come back down to earth. So John and Henry, thank you both for setting the foundation for the reason that I'm going to, behind what I'm going to show you and how we're going to get there, or how we might get there, from an evolutionary standpoint to get from Earth orbit out to the moon. So an evolving architecture for cislunar space initially starts with getting to Earth orbit, but those customers that go from Earth orbit out to GEO or GTO can be the starting point of an evolving architecture. If we put a reusable space tug in Earth orbit, pick up payloads that could be launched by these new, smaller, lower cost, but higher dollar per kilogram launch vehicles like the Firefly, that can put, the Beta is designed or projected to put 4,000 kilograms into low Earth orbit. We can move that 4,000 kilograms to a GTO, transfer, geosynchronous transfer orbit with a reusable tug. The tug comes back and waits for the next mission, and that becomes a revenue stream for the next iteration, which would be a geosynchronous transfer vehicle, which would take the payloads all the way out to GEO and allow the satellite makers to eliminate that circularization propellant from their spacecraft and get a 4,000 kilogram launched payload to be a totally operational spacecraft mass in low Earth orbit or in GEO, rather than having to put six tons or 6,000 kilograms on a spacecraft to get 3 tons into GEO. So a reusable spacecraft, a reusable space tug can move those out to GTO and come back and be refilled in Earth orbit directly from Earth. Until we have enough revenue to build a depot, a propellant depot in Earth orbit, convert water to LOX hydrogen in Earth orbit, in our scenario anyway. And now we can move payloads out to GEO and send up water and convert that into propellant. We also add additional tugs to pick up 25-ton payloads, the largest payloads that could be launched 10 years ago when we started this with the Delta Heavy and Atlas V. We can move those all the way out to GEO, or L1 rather, to build a depot out there. And the reason we picked 25 tons, besides being the launch vehicle capacity at the time, was that's the size of a Bigelow B-330 that he would like to have on the moon in the future. So we built a propellant depot in L1. Thanks, John. You know, we put it in L1 for operational reasons. We don't have to delay and wait for orbital alignment or the NASA gateway to come back around in 6.5 days to be in an appropriate location to rendezvous with it. We put it in L1 because I believe it's a strategic location for future transportation node. And we build that depot up, and then we send a lunar lander out to the depot, and we base that at the depot, and it gets refueled there. We ship water to the depot in from low Earth orbit up to the gateway in our place, L1. We don't call it a gateway, we call it a propellant depot, or it could be a transportation node, a cross-docking facility, a place to transfer payloads from one vehicle to another, a place to transfer personnel module from one vehicle to another, to use an efficient vehicle for the environment that it's in. A transfer stage, a lander, and then transfer stages around the tug to pick up things that are launched to lower orbit, bring them up to the depot. So the launch vehicle doesn't have to work as hard, or they're not designed to work that hard, and they can maximize their payload to transfer out to wherever they want to go. So that's the architecture overview, but what are the vehicles, what are the systems that we need? So first we need an Earth-to-orbit tanker to get propellant to orbit to refuel the space tug, the initial space tug. And this is all propulsive, and it just does the GTO, the geosynchronous transfer orbit insertion. Comes back to Earth orbit propulsively, circularizes, and waits for the next mission. The ETO tanker goes back to Earth and is refueled and launched again. And this tanker performs the function of the shroud on the launch vehicle as well as the payload. So we get rid of the shroud. We don't need a separate shroud. The ETO tanker is the shroud and it is the payload. Once that's operational, we take the next step and add a new technology, new capability, which is an aeroshell. So we can aerobrake back and go from GEO and take payloads all the way out to GEO with the space tug. Again, 4,000 kilograms is our target mass, because again, we're looking at the beta launch vehicle as the upper limit of a launch vehicle at a low price. Then we put in the depot. The depot is a large structure, a massive structure. If you look at the space station truss masses, they're about 1,000 kilograms a meter. But this would hold twice the propellant required for any mission, plus twice the water that we wanted to convert into propellant. So in this scenario, we're looking at probably 80 tons of water and 80 tons of propellant capacity, and up to 500 to 800 kilowatts of power. That's 5 to 8 times what's on the space station. To do that production continuously and always have propellant available, this would allow us to do monthly missions to L1, which allow us to do quarterly missions to the moon. A larger aerobrake tug gets us 25 tons out to L1 from LEO, but only 5 tons back because we have to bring people back. We did not size it to bring 25 tons back at this stage of the game. Then the depot in L1, again, this is a 70 to 100 ton capacity water and propellant on both ends. Production rate's a little bit slower because we're only going down to the moon once a quarter. And that once a quarter is 2 for cargo, 2 for people, and we're sized to put 25 tons on the lunar surface. We do need a water tanker or a propellant tanker or both to get water up to L1 or propellant, depending on whether we have the water capacity, the electrolysis capability on the depot. Depends on the staging process and how it's built and assembled. So we can use it early, or we can wait till we have the full capacity. Then the lander for 25 tons on the surface. These are all artist renderings from Brian Versteeg as my artist, except for the one on the left. That's a Dallas Bienhoff crude version of an ETO tanker. He's got that commissioned, but he hasn't gotten to it yet. And then finally, a personnel module. And we assumed it was 5 tons for people to move back and forth. We just picked that number as an arbitrary number. It uses about half the propellant in the lander to get up and down at the moon. But we can also get 25 tons up from the moon once we have a propellant supplier on the moon to get back up to L1. We can move 25 tons of water up. We can move the people round trip. And this would work the same way John described in his presentation. We can carry water back. Our numbers are about the same, depending on assumptions. Anywhere from 5 to 10% of what you produce on the moon can be delivered to Earth orbit as a saleable product, which means you have to do it for a lot less. You would only move propellant around from the moon to various places in Cislunar if it's cheaper than getting it there from Earth. So that's our architecture. That's how we would bootstrap. It's a long process. If you do it sequentially, it could take up to 40 years to get from start to finish. But it could be started at any point in the game, depending on the driving customer who wants to be the launch customer. So if NASA were the launch customer to go to the moon, we'd focus on the lander and the transfer stage out to the moon, bypass the depot on the moon, use the propellant tanker to get stuff all the way out to the lander from Earth orbit. So that's our story. We'll leave plenty of time for questions, Henry, and no numbers, no equations, but just an idea. And we are getting ready for a system requirements review, just so you know.
Thank you, Dallas. Okay, Dallas did finish fast. We've got time for, the way I want to do this, if you would, is specific questions to this presentation right now. We've got time for a few, then we'll bring the whole panel down, do any questions and comments back and forth within the panel, and then take questions from the audience. And with luck, get you off to lunch close to on time. No, that wasn't a question coming down, just coming back to a seat. Does anybody have any questions for Dallas?
I think we're hungry.
All right, Al.
Just some housekeeping in case you've done it. If not, that's fine.
All right, could you start again close to the mic?
Just a little housekeeping. If you haven't done the analysis, fine. That's not. I'm not trying to point out anything. About how long, if you lose control of the LEO depot, about how long before it comes down?
Why would we lose control? No, we haven't looked at that at all. That's a PDR, preliminary design review question later on. But it has its own propulsion. It has the tugs attached to it. It always has propellant on board. We see that as a very low probability occurrence.
Yeah, sounds pretty good. And is it very vulnerable to debris? Is there a way to?
Oh, it's absolutely vulnerable to debris. It would be protected, though, to have a probability of no penetration in the high nines, like 4, 5 nines. And they're 20-year life vehicles. These are 20-year life requirement on these vehicles.
Right.
So we'd be protect against the environment we know.
Sounds good.
Yep.
Hey, Dallas, what assumptions are you making about your LEO orbit? Like, where are you starting from?
400 kilometers, 28.5, due east out of Kennedy.
Cool. And commonality between systems?
They're all the same. All the subsystems, except for the size of the tanks. The engines would be a little bit different depending on the vehicle application, but the avionics I see could be pretty much identical across all of them.
Could you make a further comment related to that and how much money it saves and let's call it the testing, the whole chain of your system and how that helps to make it cheaper?
So the cost estimates, we use a cost estimate relationship I found in a NASA systems engineering module from 2007. We assume a 60% savings of a second-generation design, which would be all propulsive to an aerobrake solution of the same size, a 60% savings because of the design commonality.
One slight tweak on that is commonality of systems and how that saves money in terms of your avionics, software, integration and test, because there's a lot of people that don't understand
Yeah.
that.
Well, we haven't gone into those level of detail of analysis, Dennis. So we're looking at the system level in our analysis. But 60% savings overall between one version versus the next. Yes.
Question about the aerobrake.
Yes.
Am I right in thinking that you have basically a small solid disc with deployable flaps, hinges in order to...
The details are to be defined. Right now, it's just a shell of unknown quantity. We have a draft Space Act agreement statement of work with Langley to help us design the right solution.
Yeah, because there was a huge amount of work done in the mid-'80s.
Right.
Martin,
Right.
Lockheed.
And Langley's flown some test articles and done some tests on the ground for an inflatable version. I would imagine it would be likely a combination of a rigid centerpiece, like the shuttle nose cone, and then an inflatable outer ring.
Yeah, because I'd imagine technology-wise, that's one of the most, that's one that needs...
That's one of the hurdles we have to get over is get a long-lived, long reuse version of an aerobrake.
But a TLI on that is probably one of the
For
yeah, at the moment.
the best, yeah. Yes.
So something I noticed, something I noticed after a bit is you were describing that this was going to be a 40-year process.
Could be.
Just a guess from what
Yep.
I hear. And you said that the life of each module, if you will, is about 20 years.
Right.
So that means that you have to go up and either replace or maintain. Did you factor that into your architecture, or how did you compensate for the delays that are going to occur for that?
Well, we build 3 vehicles every time we build a vehicle. We would replace the vehicle after its end of life, or if it gets punctured and destroyed, we would deorbit it with our other tugs. So that's all in the process. Maintenance, we assume, is robotic. They're designed for robotic maintenance as a first order after life extension if there's a life-limiting issue or item. And we would use EVA as a backup in terms of a design solution, but not incorporate that. We have the personnel module there that can host people if they come up on a commercial crew vehicle to stay for a while. But that's in the design requirements that we would give out to our contractor.
Do those design requirements include when you when you deorbit a module, does that include deorbiting it so that it can be reused or repaired on the ground, or completely starting over?
No, we would deorbit it into a disposal trajectory, except for the ETO tanker. That's the only thing that comes back down to Earth for reuse.
Okay, thanks.
I've got a specific one for you before we go on to the panel, something we discussed in a little more depth in the lead into this. You mentioned transporting water on a routine basis rather than liquid hydrogen and liquid oxygen. Right. As I recall, the point was that there is some savings in the transport because the tankage to keep water liquid is considerably lighter and cheaper than the tankage to keep liquid hydrogen liquid and not boiling off. Yeah, it's smaller, it's lighter. I recall a figure of about a 10% savings overall being mentioned in terms of shipping and storing water, and then making liquid hydrogen propellant on demand. Could you speak to any of that in any more detail?
We ship water because it's easier to handle. It's a lower volume. It doesn't boil off. You don't have to worry about boil off for the 3 days out to L1 or for the launch process. We also have cryo coolers on our depots, so we have water and propellant on the depots. We have zero boil off on the depots. We have minimal boil off on the stages through passive cycling. We're probably down in the 0.5% a day boil off for hydrogen, as based on studies done in the past by Boeing and others, and work that's done on the ground by NASA testing.
Yeah, I gather you can reduce your hydrogen boil-off rate, but that costs you either energy for active refrigeration or it costs, more expensive storage tanks.
Yeah, that's why the depots are mostly solar arrays. You got to
If we could-
electrolyze it, liquefy it, keep it from boiling off. But the boil-off losses without the crop coolers would be about 3% maybe at the depots. So you're getting rid of that heat. 3% per day. Yeah, but you recycle that through the crop cooler and reliquefy it, so it's not a loss.
All right. Thank you, Dallas Bienhoff. And if we could call the vast rest of our panel down and grab seats at the panel table. Our absent panelist, John Goff, sent us a couple of slides on logistics and interoperability. I'm going to see if I can fish them off of my email while you guys, basically, John and Dallas, if you've got any questions for each other, now's a good time. Let me lead off with one I've got for John. Again, something he mentioned in the lead-in, which is there's a difference between the sort of reusability you get out of a rocket that has to be reused unattended and the sort of reusability you get with the logistics and support bit. John, if you'd say a word or two about that while I go fiddle with the machine and see if I can get John Goff's emails.
Yeah, the real issue comes from the fact that rockets capable of this performance are cutting-edge technology. And if you've ever seen, say, the pit crew at a NASCAR race compared to what you do when you pull up your car at a service station, you see the difference between running your performance at the limits and what you do when you're well below the performance limit. Lots of things on these propulsion systems, on these space vehicles, are going to wear out. Bearings are going to wear out. Surface coatings are going to erode on the interior of the engine, among elsewhere. You're going to get degradation of exterior thermal surfaces. Valves are going to start leaking. We know all of this from hard-earned experience, and I'm not going to tell all my war stories in this room because half of them are classified. But yeah, can you design a vehicle that can be reused a few times without serious overhaul? Yeah, absolutely. Beyond 5 or 10, probably not. Can we automate this? Can we do it all with robots? We can probably do most of it with robots. At what point does it become cost-effective, or is it no longer cost-effective to design increasingly capable, increasingly hyper-specialized or hyper-flexible robots, and just admit that sometimes you need a person with a wrench? Is something we're going to have to learn by experience, but I want the system designed to have the guy with the wrench there as soon as possible.
Yeah, I would take some issue with the 5 to 10 limit. When we designed the space shuttle main engine, our requirement was for 100 uses.
Yeah.
Or 55 starts. And our analysis was required to show that it could operate for 10 times that. And it was very easy in the engine itself to come to a point where you reached infinite life from an analysis standpoint. Now, that's in the structures, that's in the parts, that's not in the rotating machinery.
Right.
And a space vehicle is a much more benign environment than a launch vehicle. So having a 20-year, 200 mission, 100 mission requirement is a starting point. Yeah. And how much of that can we achieve? Where do we have the life-limited items that we have to worry about replacing and servicing?
Yeah. Core structure is not going to be a life-limiting item. It's not going to require extensive maintenance. Tanks, engine chamber structure.
Right.
Yeah. Surface coatings and
ducts. It's the avionics and it's the rotating machinery.
Yeah. Lots of little things, and we don't even know what half of them are yet.
Right.
Yeah, well, that gets to my follow-up question, I guess. We don't know half of them are. Do we have any feel for how you cost optimize by backing off on the performance?
That has not been explored in any significant depth.
No, because we have a lot more capability to do that in space than we do in launch.
Yeah.
The shuttle life projections were an order of magnitude higher if you went down to 80% power level instead of 100%.
Yeah, there's a few data points along that level, and they haven't been explored because if you back off 80% on your performance on an Earth launch vehicle, you don't make orbit.
Exactly,
You don't
exactly.
even bother at that point. It's only in space that we can start looking seriously at this.
It's just, with the whole 5 to 10 business, I mean, the orbiters flew 25, 30 times. Are you not counting that because of the extensive refurbishment?
Yeah, it's the refurbishing. I'm assuming that these vehicles can fly 100 times. I'm just assuming that after 5 or 10 times, you have to have either a person or a highly capable robot go over it and start fixing the things that are at their limit.
Right.
The 8-to-1 ratio of oxygen mass to hydrogen that you get in water.
Right.
The shuttle main engines had 33% more oxygen than that, and the RL-10 50% more than that. Are you assuming that it's going to be 8-to-1, and that's assuming no net helium leakage? Are you going to sell the oxygen to crew?
We use 8-to-1 in our mixture ratio assumption in our engine because I know there's a company that can manufacture an 8-to-1 engine with LOX hydrogen. At least they've done that in the small scale in the attitude control size. But their engine cycle is such that they could apply that to a large vehicle, a large engine. And we're not talking launch vehicle engine sizes here. We're talking probably 1,000-pound thrust engines and multiple engines. So I assume 8-to-1 engines once we have the depot in place. It doesn't matter until then.
Yeah. And I agree with that. I think we probably can go 8-to-1 for the relatively low thrust engines we're talking about here, where an RL-10 would be considered the largest engine we'd consider. For the purpose of my math, I did everything at 6.5-to-1 because until the depots are up and running, that's about where we'll be.
Right.
It changes things a little bit if you go to 8-to-1. And then there are some other options that we can use if for whatever reason an 8-to-1 engine becomes a showstopper. One that I looked at a little bit is running it at 6.5-to-1, but then that leaves us with a bunch of extra oxygen on the lunar surface. We can run that through liquid oxygen aluminum hybrid strap-on boosters to boost the performance of that lander and get back what we lost with the inefficiency there.
When you did your analysis, and I really appreciate the analysis, gateway focused, you had a little bit about low Earth orbit. We did an analysis of the EUS, that if you made the EUS a Super Centaur, call it, with the ACES IVF system, that you could actually get the Orion into low lunar orbit. And then you can also refuel the EUS, and the EUS becomes a supersized, call it a Super ACES, reusable stage. When we ran the numbers, we got 8x payload to C3 plus trajectories. And so when you did your statement of work, I don't know if NASA paid for you to do this, but when you did your statement of work, did you look at any alternatives other than just gateway and going to gateway orbit or
I looked briefly at a wide range of cislunar orbits, like I said, L1. I even looked at low lunar orbit in case that turned out to be better, and it turns out that it doesn't give us any advantage. It's actually slightly worse. So in terms of orbit, I looked a little bit at everything, and I said gateway is good enough, and it's where NASA plans to build the first piece of infrastructure, so let's just focus our analysis there. In terms of vehicles, I looked at the smaller 10, 15-ton scale vehicles because that's what NASA wants near term. I looked at ACES because that seems to have some degree of reality, and I can borrow numbers from ULA from that. The idea of a super EUS, I hadn't actually considered that. That is interesting. That would take us way up in propellants and payload scale, so it would be difficult to support in the nearer terms, but farther out, if NASA happens to leave a spare EUS somewhere up in lunar orbit, I might just grab it and hold on to that for the day that we can use it.
Dennis, back on Constellation to your question, when Constellation and Ares 5 and Ares 1 were around, we looked at refueling the upper stage on the SLI with Constellation Ares. We looked at refueling that and doing the mission with NASA's hardware. We could take the landed mass on the moon from 18 tons to 51 tons if we refueled that in Earth orbit and then used and didn't do any more refueling.
Yeah, but your former masters don't allow that anymore. But also, just to follow up, when you showed your masses to TLI and all, NASA's HLS procurement documents all show 15 tons for these commercial vehicles to TLI, and it doesn't look like, even from their own documentation and from what you did, that they make this. So we've got a gap in the architecture.
My numbers come in at about 14 to 1 or 14 tons to TLI, where NASA is assuming 15. So there is a small gap there.
It's not small at TLI.
Yeah, well, I can make everything up here 7% smaller and it'll fit. It'll still have useful capability. Or possibly my analysis is wrong and they really can deliver 15 tons. I haven't been able to get deep enough into SpaceX's numbers to rule out that possibility. We're pretty close to making it fit. I'm confident that one or the other ways will eventually.
Yeah, that procurement painted a very tight box in which a commercial company is supposed to operate.
Yeah.
Yeah, so in your analysis early on, you dismissed a couple of the new rockets, like the SLS and the BFR.
BFR, Starship, Super Heavy.
I understand the BFR because it's a little bit further out there, and like you said, there's no market. It's not 100% sure. The SLS seemed to me like a very well-funded program, and NASA is basically taking components that were reusable and making a conscious choice to make a non-reusable vehicle and launch system out of them, because it makes more sense to do so in terms of the missions they're interested in. So I'm curious why you didn't include the SLS even as a point of reference in all your analysis, and if you have actually analyzed it, and if you could say where it fits in terms of the analysis. I mean, you dismissed it because it was not reusable, but it seems like...
I'll actually take this job because there is no likelihood I will ever be in a position to get a contract that NASA influences anyway. It's a political question, and I'm a political person in my day job, so I might as well take this question. I did a quick analysis on SLS, and depending on how you figure costs, NASA likes to quote the marginal cost of launching one. My approach is to take the rough ongoing program cost for SLS of roughly $3 billion a year and assume it will continue, then assume that they'll probably, if they're lucky, be able to launch one a year under that. Leaving aside another $1 billion a year for the Orion, that's $3 billion to put about 70 metric tons in low orbit. I believe, without having the numbers in front of me, that worked out to some tens of thousands of dollars per pound delivered to low orbit versus a Falcon 9 reusable at this point being on the rough order of $1,000 to $2,000 a pound, depending on how well you haggle. The bottom line is that SLS is just really too expensive to be using in large numbers for major parts of a project that you want to be affordable. It's an interesting and even a magnificent technical achievement to take all those components from the shuttle program, rework them, and put them into a launch vehicle, but it's not a practical business over the long run, in my personal opinion.
I will add to that NASA will probably build a small number of SLSs just to avoid saying that it failed completely. They may build a modest number if it works better than Henry is anticipating. If they use some of those to put the initial gateway architecture up, that gets us bootstrapped faster. If they use some of them to send NASA astronauts to visit the gateway and say, we're doing stuff on the moon, that's fine. That helps. I just don't want to depend on it.
Well, this seems to me like a bit of a dismissive answer. So I'm going to kind of encourage you guys to take a closer look.
Cost is not a casual question. Cost matters if we want to go up there sustainably, and it's an extremely expensive rocket.
I think you're starting with the assumption here that they cost more. And if you actually look at the numbers in terms of what NASA has to pay SpaceX, for example, to launch a rocket or put payload and people in orbit, compare that even to the space shuttle, what it costs to put people and payload in orbit, you'd be surprised. They're closer to on par. Sometimes the space shuttle is even cheaper for certain missions.
Let's leave that one at there are varying points of view on that, and move on to things specific to this panel.
It is very specific because I'm asking why we didn't include the SLS into the system, and I think I'm hearing, if I'm not correct,
it will get used.
Or not reusable.
It will get used, but to a limited extent. But it's really too expensive for people who are planning something that's sustainable in the long run to bring in voluntarily. That's a political answer. I'm a political person.
Right.
I don't expect repercussions.
Reasons.
If we could move on to the next question, because we are running low on time. Thank you. But yeah, that is That is going to be a question. How much does SLS cost? It's not a very particularly well-fixed target, but it's a very high target. Anyway, next question, please.
Dallas, what technology development is needed to support your infrastructure? For instance, propellant transfer comes to mind.
Right.
And what research could SSI help support to move it along?
The technologies needed for the first step is to fly what we know, which is what we designed to do back in 2012 for cryogenic propellant storage and transfer. Thermal insulation, propellant transfer valves, cryo transfer valves, and the engines. We're going to need the engines not to operate 8-to-1 initially, but eventually. Those things were ready to fly and space test in 2012. There have been more ground tests since then, so they're more ready to fly now. They haven't flown. So I propose that we can build the first step in our architecture with the stuff we know today. It's the next step with the aeroshell, where technology is a hurdle to overcome before we can operate that. And then the water electrolysis, that hardware is available commercially. It hasn't been tested in zero-G, but they build their solid oxide electrolysis cells that are available on the market today. Two major companies. There's one going to Mars on Mars 2020 to get water out of the atmosphere and carbon or oxygen out of the atmosphere as a demonstration. The liquefaction stuff has been tested on the ground for oxygen at 90 degrees. I believe the hydrogen tests have started, but have not been completed. There's a company that I work with on that. So those are the steps that need to happen. And then large solar arrays, we can get those on the market today. So very few hurdles that are showstoppers in that architecture that haven't been tested on the ground today. None of them have been tested in space. Yeah.
So, mild question using the SLS. I know that we focused right here our discussion on reusable and sustainable systems, but the fact is the SLS will be in use. There's motivation for Congress to keep their constituents happy and all of that. So the answer you gave was that SLS will help along, like if they want to send a piece of the gateway, that will help speed up the process. My question is, can you quantify that? If the SLS were to help out, say, twice, 4 times, however many times, how can we quantify this in terms of gain, and how can we explain this, for example?
That's a tough one, and probably the biggest unknown is to what extent can we talk NASA into doing things like putting propellant depot on the gateway. Because if they use 2 or 3 SLSs, and if they design the gateway to really support everything we need to build from there, then we're done as far as the gateway is concerned. We get that stage of the infrastructure in place for free. That would be pretty huge, particularly insofar as once that's done, the business case for building everything else becomes much easier because you don't have a big hole in your business plan saying here, and then a miracle occurs. You can point to the gateway. So using the SLS to build a fully functional logistics base in cislunar space would be pretty huge. If they don't do that, we can still do it, as I've shown, using Falcons or New Glens, but that would be huge. Beyond building the gateway, the question is that the issue is that the SLS is a NASA vehicle that's going to serve NASA priorities. It's highly unlikely that anybody other than NASA will ever buy an SLS. So what are they going to do beyond building the gateway that would be of great interest to us? They might do some lunar surface development using SLS-scale payloads. That could be helpful. It's a bit more speculative about their priorities aligning with the long-term development that we're talking about here. But that would be where I'm looking next. They'll probably fly astronauts around doing cool things because astronauts doing cool things is politically good for them. Many of those would not align with what we're trying to do here, but then I'm not going to take it away from them. It's worth doing for its own reasons.
The short version of the answer to your question is the entire program at this point is a work in progress and a moving target. Exactly what part SLS is going to play with that is also a work in progress and a moving target. The only real answer you can give is it depends on a lot of factors that you can't pin down at this point. It'll be interesting to watch it all unfold. It's an exciting time to be alive because something is unfolding, is all I'll say on that. John Goff, who can't be here, did manage to send us a couple of slides.
Henry, before you jump,
Alice, take it away.
the NASA program for going to the moon today, as I understand it, the SLS and Orion get the crew out there, and they can have the capability to take about 10 tons along with them as a co-manifested payload. So if they were to combine Gateway modules with the crew trip, then the maximum size of any one module at the Gateway is 10 tons. Might be less, but that's kind of an upper limit. All of the procurements that were talked about by John for the transfer vehicle, the refueler, the lander, those are all slated to be owned by the companies that build them. NASA's not going to take ownership of them, and it's up to those companies to decide how they will get launched. So they have the opportunity to use any vehicle they want. Could be SLS, they could say, I can co-manifest or not. Could be Falcon 9, could be New Glenn. But it's up to the companies that are going to get the procurement opportunity from NASA to decide how they will be launched.
Thank you.
Okay, sorry.
John Goff did manage to send us some slides talking about logistics and compatibility and so on. So we're all seeing this for the first time. And also he sent them in PowerPoint X instead of PDF, and my ancient machine is not entirely digesting it. I have to leave it in the viewer to switch between them. But it is first, on first glance, and I'm curious if anybody on the panel has any comments about this. He talks about, in terms of interoperability, while our panel is looking over what he sent, let me comment on that. One of the advantages of a distributed system of the sort we're talking about, with transfer points and different types of vehicles and different types of missions being flown, is that it can be done incrementally. Commercial outfits can do one particular part of it, say on a NASA contract to start, and then hopefully develop commercial customers for it too. All the pieces, the corollary to that is all the pieces need to work together to the degree that if your tanker is showing up at somebody else's depot, you need to have compatible fluid couplings. You need compatible communications, compatible grapple fixtures, and so on. John Goff is an expert in that sort of thing, and this slide, to the extent it's visible, is quick summary of the big picture in terms of compatibility on that sort of thing.
Yeah, no, John is right, which is why we look at the entire architecture, not just one element or one system in the architecture. They have to work together, they have to be designed together, and they have to be compatible. So it's best to look at the whole architecture, not just one or two elements when we go to these integrated missions.
Yes, another thing that I think I'm reading here, and it's something that I hadn't actually thought of before, so thank you for getting these charts, is that the vast majority of our docking interface work to date has been done for manned vehicles. Mm-hmm. And even when we do something like an unmanned Progress or an unmanned Dragon docking with the ISS, we're basically using a manned vehicle docking architecture for that, even though one of the vehicles is merely pressurized but not actually crewed. And John is suggesting that when you start designing specifically for tankers or other unmanned, uncrewed vehicles, the architectures are going to look different, possibly easier. Some of the requirements, the forces are reduced substantially if you don't have pressurization loads, but definitely different, and that's not something that anybody has been seriously looking at.
One of the things Altius does is work on very flexible low-mass grappling fixtures and grappling hardware for general use, in causing one satellite to come up to another one and be able to fix its position relative to it without anything as complicated as a pressure tunnel attachment. Dallas, do you have anything more you want to say on this? I was going to round this out by putting up a quick plug for Altius. This should be some pictures of some actual products they've got available or are working on. As I said, if you have needs in all of this, they're available. Again, if you're willing to involve money in the equation, you can get a lot more detail from them than you're going to see in this session. They've something called the dog. I promised John a plug in exchange for us, devouring his time like piranha. Something called the dog tag grapple fixture, which you went about at more length at the last Space Access Conference, has multiple modes, as I recall: physical contact, including the ability to actually hit it with a harpoon type of thing, punch a hole in it and grab it that way; magnetic contact, all in one very lightweight fixture that's available now. MagTag modular interface ports, multiple versions, power, data, fluid transfer. Anyway, Altia Space out in Colorado, John Goff, not the only outfit that's doing this sort of thing, but yeah, they're among them and they're worth talking to. Any closing thoughts, gentlemen?
Let's go have lunch.
That's the best closing thought I've heard in a while. Thank you very much. Lee?
I would just point out that SSI made the initial investment in Altius.
And a very good investment it was.
Yes.
Wasn't aware of that, Lee. I'm
you.
guessing you influenced that. Thank you.
Okay, one comment before we break for lunch. Some of you have purchased lunch, others have not.